Hello, all. Hope you're doing well. So, we are going to discuss about indicators in acid basis salts, lecture 4. So, indicators are chemical compounds which has a distinct color in acidic solution and a different color in basic or neutral solutions. So, when we talk about types of indicators, we have acid base indicators. We can even classify them as visual indicators also. Then, olfactory indicators. Olfactory indicators are those which are going to show some coloration, which show some, you can say, there is some change in odor. So visual indicator is something that you can see. So we are going to discuss few things over here. We are not going to go in depth of indicators. So I'll be making a separate video of indicators later on. So olfactory indicators are substances whose odor changes in acidic or basic solution. So olfactory means smell. So if we have any person which is visually impaired, so with the help of smell they can actually detect whether the solution is acidic or basic. Then acid base indicators, visual indicators, we have litmus that we are studying right from lower grades also. So red litmus to blue, that is in case of bases, and acids we have blue to red. So I always remember like this, that acids A to B, right? So sometimes it's confusing, but it's okay. Everybody has their own way to remember it. So then we have phenolphthalein. Phenolphthalein is very colorless liquid. So it remains colorless in case of your acid, but yes, in case of base, it changes into pink. So methyl orange is there. So one by one, we'll be discussing about all these. So examples of olfactory indicators, we have vanilla extract, we have clove oil, raw onion. So many examples are there, but I've taken only few over here. Then we come to, so litmus we have already discussed. So let's say we have our acid and we have our base, and we are going to discuss about some of the indicators over here. So litmus we have already discussed, changes blue litmus to red in acids, then red to blue in case of base. Then we have phenolphthalein. So phenolphthalein is going to remain colorless. See, litmus is actually some sort of purple color dye. So it's obtained from uh, lichens, whatever you want to pronounce. So phenolphthalein is colorless, and in base it changes from colorless to pink, and originally also it is very much colorless. So we have some more indicators that we can write over here. We have red cabbage leaves, which is originally purple in color, but it can be pink or red in acid, and green, yellow in case of base. Then we have beetroot juice. So this is again purple in color. In case of acids, it will remain purple, but in case of base, it will be yellow. Then we have China rose solution. So that is magenta in base and green in case of, sorry, magenta in case of acids, my mistake, and green in case of bases. So this is China rose solution. This is originally red. Then we have universal indicator. So universal indicator, like it depends upon the coloration. So it's red in strong acids, but it can be orange, somewhere orange to yellow in case of weak acids. In case of bases, it is blue or purple. So again, weak if we have, then it is blue, purple in case of strong base. Then original color that we have for indicator, that is green. Then we have, now these all indicators work on the basis of certain pH. pH we are, like you have studied in your lower grades also, but we'll be doing it in the next video, not in this one. So if we talk about some more indicators, we have, see, most of the indicators, like if we say thymol blue is there, that is methyl orange, Congo red. These are all dyes, right? So, but like again, they show some coloration in case of acid and base. Again, there is the different kind of chemistry involved over there, but we'll be discussing later on. So, thymol blue is another indicator. So, we are going to study its acidic range over here. So, that is red or yellow. Then we have basic range. Even indicators can have some pH range. So the basic range is yellow to blue. Then we have bromophenol blue. Its pH value is going to be somewhere around 6 to 7 that we have taken. So in acid, it's going to show yellow, and in case of base, it's going to be blue. Then methyl red, that is red in case of acids, and yellow in case of bases. So I think this is enough for indicators. And yes, one more we can discuss is about turmeric. So turmeric is very much yellow. In acids, it will remain yellow, but in case of bases, it will change into orange, or not orange, let's say reddish brown. Then we have methyl orange. So methyl orange in case of acids, it's going to be red. So then it is not going to change in color in case of bases. Now we have like if we talk about olfactory indicators, so let's say if we have vanilla essence, right? Vanilla extract or vanilla essence we have. So this retains its smell in acids, but in bases it loses its smell. And same we can talk for raw onion. Raw onion also retain its smell in acids but loses its smell in case of bases. That's how you can remember it. Then about turmeric, it's like if you have a yellow stain on any kind of fabric. So in acids will never change, you can say, the color of turmeric, but bases, like how we can actually prove it that it changes into reddish brown. So you have soap. Soap is majorly base in it. So if we try to clean a fabric which is having a stain of yellow turmeric, so it changes into reddish brown. So again, due to a chemical reaction between, you can say, the turmeric and the base which is present in the soap, that's why its color changes into reddish brown. Then we go to the physical properties of acids and bases. So we'll do acids first. So first thing, we know it has sour taste. Then indicators effect we have already discussed. Then we can even discuss about effect on skin. or we can discuss about electrical conductivity, and then we can discuss physical state. So it's not always that you have all the acids in the form of liquids. Some can be solids also. Some are volatile liquids. Volatile means they can form vapors very much readily. So we have highly corrosive acids. So generally highly corrosive acids we never taste. So the weak acids we can taste. So vinegar we can taste, sour taste. Effect on skin. Now we are effect on skin. We are going to discuss on the base. You can say majorly concentrated acids. So if we have concentrated sulfuric acid, so they have a lot of corrosive action on skin and painful burns can happen. So concentrated sulfuric acid, it stains black, the skin color into black. Then concentrated nitric acid, yellow color of the skin. Concentrated hydrochloric acid can be brown or amber colors. And if we talk about carbonic acid, which is not corrosive at all, it is there in soft drinks, we are consuming it, but definitely it is damaging to the body because it's an acid after all. Then we have electrical conductivity. So most of the mineral acids, so I'll be writing it over here. Most of the mineral acids are good conductors of electricity. So again, just like we have strong acids and weak acids, similarly, if any strong acid is there, its conductivity will be higher. It will be a good electrolyte. That's what we call them as good electrolytes or bad electrolytes. So electrolytes can be anything. It's not only acids, it can be bases, it can be salts, it can be any other compound which can ionize itself in the presence of water. So electrolytes, good, you can say, are substances which can conduct electric current. So most of the mineral acids are good electrolytes, but if we say carbonic acid, which is a weak acid, so it won't be much of a good electrolyte or good conductor of electricity. So now on electrolysis, since we are talking about electricity, so obviously an acid is undergoing decomposition. If you go back to chemical reaction and equations types, so in the presence of electric current, it's going to decompose. And if it is decomposing, it's going to decompose into hydrogen. And where does hydrogen deposit, or you can say is obtained in the electrodes or in the chemical process? It's going to be it at cathode. So we can write this one single line: on electrolysis they decompose, liberating hydrogen at cathode. Cathode is a negatively charged potential. Now we move to physical properties of bases. So they have bitter taste, we know that, and soapy to touch, slippery sensation will be there. Then indicators effect we have already discussed, and then effect on skin. So they are mildly corrosive on skin, not much. So we don't have much for you can say for the bases, but now next that we are going to discuss is chemical properties of acids. So, first one, metals react with acids, any acid. So, let's take in general hydrochloric acid, or you can take sulfuric acid. So, metals reacting with acid are going to give us salt and hydrogen gas. So, we can take multiple examples. So, we can take zinc over here reacting with HCl to form ZnCl2, zinc chloride, and hydrogen gas is formed. Then we can take magnesium reacting with HCl, forming MgCl2, and hydrogen gas is evolved. Then, second reaction, we have acids reacting with metal sulfides or bisulfides. So, if your memory serves, sulfite is this, that is SO3 2 minus. Bisulfite is HSO3 minus. So, these ions we are talking about. So, now if we have taken HCl and we can take calcium sulfide, so we will get calcium chloride, water, and sulfur dioxide is going to be formed. And similarly, you can even take calcium bisulfite over here. So either with bisulfite or with sulfite, you will get exactly same products, the salt, so and water. So you can just acids plus metals. So this is going to give you salt, water, and sulfur dioxide. You can remember the main parent reaction and then you can write an example. So then we go to acids reacting with metal sulfides. So they are going to form salt and H2S gas. So it's a type of double displacement reaction we are discussing. So metal sulfides, or even it can be bisulfides. So let's take metal sulfide. So sulfide is S minus 2, bisulfide is HS minus. So acids, we can take sulfuric acid for a change. So metal sulfide, we can take sodium, or you can take sodium bisulfide, NaHS. So it will form Na2SO4, sodium sulfate, along with what? H2S. So H2S is a gas, it's a weak acid, and it has a characteristic rotten egg smell. So you can take multiple examples, at least if you remember the main reaction. Then we go to next, acids reacting with metal carbonates, or we can even take bicarbonates. So it's going to form salt, water, and carbon dioxide. So acids, we can take nitric acid for a change, and we can take potassium carbonate, or you can take potassium bicarbonate, KHCO3, and it's going to form potassium nitrate, so its own salt, if you can see this, along with water. And since you have taken a carbonate or a bicarbonate, carbon dioxide will always be formed. And do remember, how do we get carbon dioxide in aqueous solutions? That is with uh, effervescence, that bubbling I told you when you open any cold drink bottle. So it produces a fizz sound, that is effervescence. Then we go to next. So acids reacting with metal chlorides. So they are going to form another type of salt and another type of acid. So the acid, it depends upon like what salts you're taking. So if we uh, if we have an acid with a metal chloride, so H2SO4, so obviously we want different acid. So NaCl, it's going to form Na2SO4 plus HCl. Now this is a main reaction. It's a double displacement reaction, but it happens in two ways. So if you take, I'm going to erase it. So if the temperature is below 473 Kelvin, so then we are going to get bisulfate, sodium bisulfate. So if you can see, this H2SO4 is dibasic in nature. So because its basicity is 2, so this replacement of hydrogen is not going to take place just in one go. It's going to take a two-way step. But again, it depends upon the temperature. We will get the end salt as sodium sulfate only, and along with that, you will get HCl. Again, it's a double displacement reaction in the form of gas you will get. Now, the second step, NaCl reacting with NaHSO4, that is above 473 Kelvin. So this is going to give you sodium sulfate along with HCl. So since H2SO4 is a dibasic acid, so its basicity is 2, that's why this is happening based on the temperature. So the temperature is not going to rise just in one go. There will be temperature below 473, then above 473 you will get a salt sodium sulfate. With below 473 you will get sodium bisulfate. So you remember, this is a very important, it can be an objective question, that if acid is reacting with metal chloride, then the bisulfate, or you can say the bi, can be any bi compound. Usually it's always sulfuric acid. So which kind of salt will be formed over there? So below 73 Kelvin. So they can twist and turn and they can ask this objective question to you. So this is one of the important aspect. Now similar to this, we have another equation. So next is acids reacting with metal nitrates. Now, since they are nitrates, so they are going to form HNO3 as a different acid. So over here it was the acid we are, since it's chloride, so we are getting HCl over here. So nitric acid and the salt. So we have taken sulfuric acid again, metal nitrate, you can take sodium salt, NaNO3, below 573 Kelvin will give you sodium bisulfate, same salt, and HNO3, different acid. Then if we take NaNO3 again, make it react with sodium bisulfate. You can even take these two reactants, just write the temperature above 573 Kelvin. That will also work and it will give you sodium sulfate plus HNO3. Both ways are okay. You can write like this also in continuation, or you can just write, even over here I did the same thing, but you can even write sulfuric acid plus NaNO3 gives you sodium bisulfate. It's in the second reaction also you can use this same reactants and you will get sodium sulfate and HNO3. You can do that way also, that's not a problem. Then we go to next reaction. So acids reacting with metal oxides. So metal oxides are also basic in nature. We have to make sure that oxides that we are taking has to be in basic form. So metal oxides will form salt again and water. So it's a type of neutralization reaction. Just that we haven't taken hydroxides over here, but metals are basic in nature, most of them, and metal oxides are also basic in nature, again most of them. But we have certain oxides where like specifically, metal oxides, there can be amphoteric oxides also, that I'll discuss after finishing the chemical properties of bases. So acids, we can take HCl, making it react with sodium only will take Na2O, so it will form salt NaCl, if you can see over here, and water is going to be formed. So we can actually take some other salts, take some other oxides also. Now, last reaction is neutralization reaction. So, acid base neutralization. And please remember, neutralization reaction is exothermic in nature. Then we can take our HCl base, you can take potassium hydroxide, will form potassium chloride, and water is formed. So now before moving to this chemical properties of bases, let's discuss about this part. Non-metal oxides. Now non-metal oxides can be of two types. One are acidic, another neutral. So acidic oxides are basically what? So they react with water to form acids. That's why they are called as acidic oxides. Now, what are neutral oxides? So, neutral oxides are those which do not form acids, which do not react with water to form acids, and we don't have many. So, we'll take this example, carbon dioxide reacting with water to give you carbonic acid, H2CO3. So, we even call this carbon dioxide as anhydride of carbonic acid. So, what's an anhydride of carbonic acid? What's an anhydride? Anhydride means without water. So, what is an anhydride of sulfuric acid? So, we can write more reaction. SO3 reacting with water will give you H2SO4. So, SO3 is an anhydride of sulfuric acid. So, we have to remember which oxides are giving what acid. So, SO2 reacting with water will give you H2SO3 sulfurous acid. Then we have P2O3 phosphorus trioxide reacting with water to give you H3PO3 phosphorus acid. P2O5 reacting with water will give you H3PO4. This is phosphoric acid. So if somebody is going to ask you what's an anhydride of phosphoric acid, so the answer is phosphorus pentoxide. What is the anhydride of phosphorus acid? Answer is phosphorus trioxide, and we can even use for nitrogen dioxide reacting with water. So they give a mixture of acids, nitrous acid or HNO3. So both acids can be formed, nitrous as well as nitric acid, and the anhydride is NO2. Now again, nitrogen oxides, we have many. There are many reactions, so that I'm not going to discuss over here. But yes, few of them you can remember that what is a anhydride. You can say they are all in the, you can say, gaseous form. So what is anhydride without water of acids? So this can be a very good question in the objective, in the multiple choice questions. Then we have neutral oxides. So water itself is a neutral oxide. It's an oxide. It's a oxide of hydrogen. So then we have carbon monoxide, which do not react with water to give you any acid. We have NO, which is nitric oxide. This doesn't react with water to give you any kind of acid. Then we have N2O. N2O is called as nitrous oxide, and this is also called as laughing gas. So this is a neutral oxide, doesn't react with water to form any acids. So you have to remember these examples. This is one of the most important topic that you should know. Then moving to metal oxides. So metal oxides are of two types. One is basic oxides, obviously when they are reacting with water to give you bases or alkalis, and another is amphoteric oxide. Amphoteric term is something very common in chemistry, meaning dual behavior, dual characteristics. So basic oxides react with water to give bases or alkalis. So you can have sodium oxide. You can write the equations on your own. It reacts with water to form sodium hydroxide. See, remember one thing. Now I'll write it separately over here. Metals reacting with water will give you base and hydrogen gas. But if you have a metal oxide reacting with water, it will give you only base. It's not going to give you hydrogen gas. Just remember these. Like most of the time I've seen a couple of students getting confused. It's metals reacting with water to give you base and hydrogen. Metal oxide reacting with water will give you only base. There will be no hydrogen in the second reaction. So sodium oxide is there, magnesium oxide is there, then we have potassium oxide. You keep on writing. We have calcium oxide, right? We have so many other, sodium, magnesium, calcium, potassium. So I'll just write etc. So these are going to react with water, but we don't have many alkalis. Just remember that. Then we go to amphoteric oxides. So these are oxides which can react with both acids as well as bases. So let's take an example of zinc oxide. Zinc oxide can react with acid to form salt and water. It's amphoteric in nature. And zinc oxide can also react with NaOH. Now it's going to give us a different kind of salt. So in the future lectures of acids and bases, we'll be discussing about different types of salts also. So it's going to give us Na2ZnO2 along with water. So this is called as sodium zincate. So it's a different kind of salt, but again, it's a type of, you can say, neutralization reaction only. So over here, zinc oxide is behaving as an acid. Over here, zinc oxide is behaving as a base. So that's a dual. So it can react with acids as well as base, right? So then moving ahead to chemistry of bases, chemical properties of bases. So metals reacting with bases to give you salt and hydrogen gas. So we have taken already zinc. We can take aluminium, amphoteric. You can take a normal metal also. So now since see we can't take actually normal metal over here because it's reacting with base. So we have to take amphoteric only because metals cannot just react with base. Normal metals cannot just react with base. It has to, they have to be little different. They have to be amphoteric, only then they can react with bases. So aluminium can react with NaOH to give you sodium aluminate along with hydrogen gas. Then quickly moving to next reaction. So base reacting with air. So air, what do we have? Carbon dioxide. So again, it's going to form salt and water. So remember about this thing, NaOH. This is hygroscopic in nature. I'll be discussing about these terms also. Hygroscopic means it can absorb moisture from the surroundings. So usually when you are in a lab, NaOH pellets are there in the airtight container. So when you weigh those pellets and you want to make a solution out of it, so quickly you can see if you are going to keep it in the open air, so they will absorb moisture and they will start changing into some liquid form. So again, because of this property of NaOH, so they are hygroscopic in nature. That means they can absorb moisture from the surroundings. So NaOH can react with carbon dioxide which is present in air, forming its salt Na2CO3, and water is released. So even this reaction can happen if you have NaOH, and obviously carbon dioxide we have a lot in our air, right? So it can react to give you salt and water. Then again, next reaction is reaction with acids that I'm going to skip because I've repeated a number of times the neutralization reactions that you can do it on your own. Then we go to the next reaction. So bases reacting with ammonium salts. Now ammonium salts are acidic. Now why they are acidic we can actually discuss in the salts part. So they are going to form salt and water, and even ammonia gas is released. So let's take our favorite NaOH again, and ammonium salt we can take NH4Cl. So it's going to form NaCl, water, and ammonia gas is released. So now this we need to remember that if you're taking ammonium salts along with bases, so definitely ammonia gas is going to release, okay? Because you can say it's a double displacement reaction only. You're getting salt in water, but additional ammonia is also getting released because you have taken ammonium salt over here. Then We go to next. We have our bases reacting with heavy metal salts, forming salt, and this reaction can be a method to prepare insoluble bases also. So we have our favorite NaOH again. So heavy metal salts, basically you can say the middle block periodic table you have seen. From the left and right, group 1 and group 2 is there. So the middle block, 3 to 12 groups if you see. So most of them we are considered as transition metals, heavy metals. So heavy metal salt. So I'm going to take zinc sulfate over here. So again, it's a double displacement reaction. Sodium sulfate will be formed along with zinc hydroxide, which is an example of insoluble base, and it's going to form white precipitate. So we can take multiple examples over here. We can even do it with iron, NaOH reacting with FeOH whole twice, ferrous hydroxide. So, sorry, my mistake. So the salt we have to take Fe2SO4 whole thrice we can take. This is ferric sulfate. Even ferric hydroxide is also Na2SO4, so I'm not balancing it, that you can do on your own. So FeOH whole thrice. So this is ferric hydroxide. Ferric hydroxide is reddish brown precipitate that we discussed before also. Then we go to another reaction with the iron salt again, FeSO4. So iron is having oxidation number of +2. Over here it was having +3. So in most of the double displacement reactions, the oxidation number doesn't change much. Then we have Na2SO4 again, sodium sulfate, and FeOH whole twice is going to be formed. And this is ferrous hydroxide. This is dirty green precipitates. Again, I discussed before also. So again, so I have taken a lot of time in this lecture, so I'll stop over here. So I hope you have understood these chemical properties. There are a lot to discuss in acid bases and salts, so we'll be discussing in the next video. So till that, please like, subscribe and share, and you can even comment, and you can even write what kind of videos you want. But I'm following a sequence, so I'll be finishing ninth and 10th grade syllabus, then I'll be moving to 11th and 12th. But yes, any kind of comments are most welcome. Thank you for listening.